All right, guys, welcome to today's lesson on solubility products. So obviously it has to do with, substances dissolving, having to do with solubility. Got Mr. Potato Head and his wife here. She says, I see you looking at that French girl. Okay. Solubility products. This is where that term comes from. When you guys think products, think about multiplying, right? Think about if you have a salt or a solid that is to some measure soluble in water, right? So we take our barium sulfate, which is a salt, it's a solid. It can undergo a reversible reaction in which some of it dissociates. You guys notice it becomes aqueous. So this would be it dissolved in water, and this and whatever amount remained as a solid would be the part that was insoluble. Now you guys know we can come up with an equilibrium expression, right, for any reversible reaction. Remember, you include aqueous and gas states because those are ones whose concentration can change. So if we were to do the solubility, remember it's the products over the reactants, that's where the product comes from. So we get concentration of barium times the concentration of sulfate, and then you guys remember we don't include solids, so the K value, notice it's called SP. SP is just for solubility product. Once again, it's just a K. You guys remember like when we had the equilibrium constant for acids, it was Ka, for bases, Kb, for waters, Kw, for solubility products, KSP. So just think about a substance dissolving in water. This would be, so if I take the concentration, once it's reached equilibrium, right? You guys know, right? You put it, it's going to reach equilibrium. There's going to be a point at which this concentration stays constant. If I take the concentration of the barium ions times the concentration of the sulfate ions, that's what's going to equal my solubility product constant. KSP is not the same thing as solubility, though the KSP will tell you, it'll give you information about the solubility, like as you might expect. Right? When you're doing the KSP, if you get a KSP value and it's very small, that must mean that these concentrations are very small. It must mean it's relatively insoluble. So a low KSP value would correspond with a low solubility, and on the flip side, a high KSP value would indicate, right, much of the salt readily dissolves and is in its ion state, and so these values would be large, indicating it had a high solubility. So KSP and solubility aren't the same thing, though they do correlate with each other. Solubility is generally expressed as the mass of solute dissolved in 1 liter. So you can grams per liter. What's another one? Moles per liter. That would be your typical solubility. We're trying to show how much can dissolve, in a certain, and usually it would be per liter of solution. So for example, let's do a problem. Notice this is in purple, so this is where I want you guys to definitely include in your notes. What's the molar solubility of lead chloride at 25 degrees Celsius? And you guys can see we're going to indicate it's at what particular temperature, because you guys know the solubility is indeed affected by the temperature. Generally speaking, for solid solutes, the higher the temperature, the higher the solubility. So we're given the KSP value, and you guys notice, look at what the KSP value, 1.7 times 10 to the negative 5. What does that tell you? Very small number. So what does that indicate? Oh, it's probably not very soluble. So what am I predicting when I get the molar solubility of lead chloride? I'm expecting a low value. Okay. So what are we going to do? You guys, here's our reversible reaction, lead chloride. Some of it's going to dissociate. Obviously, it's heavily favoring this side, as indicated by a low KSP value. So then, if we want to get, what we might want to do is, if we have the KSP, we might as well set up the equilibrium expression. Right? I got KSP is equal to 1.7 times 10 to the negative 5. When you guys agree it's equal to the concentration of my lead ions, right, times the concentration of my chloride ions. But what do I have to do? You guys remember, raise it to the molar coefficient. I have to square it. So I don't know how much of this dissociates, right? You guys remember, if we don't know how much, what do we call it? We can call it X. So let's say a certain amount, like for every one of this that dissolves, I get one of this and 2 of those. So I'm going to just set up my thing like this, 1.7 times 10 to the negative 5. I don't know what the concentration of my lead ions are. I'm going to call it X. So, right, some of it, I'm going to produce a certain amount of this. Well, then what's the concentration of my chloride ion? For every one of this, I get 2 of those. So notice the concentration of the chloride ion would be 2X. Now this is what a lot of students forget. You guys, this is 2X. You also have to, according to the equilibrium expression, you also have to square it. So So not only are you doubling it because it's 2 for every one of that, you're also squaring it to make the equilibrium expression true. And then I continue to do my work. 1.7 times 10 to the negative 5 is equal to, you got 2x squared, you have to square both, so it's 4x squared. 4x squared times x is 4x cubed. You guys, this is why you do math or algebra in other classes, so that way you can apply it in a real subject like chemistry when you're actually trying to do a problem solving. So now it's just a matter of solving for x. I divide by 4, and then what would you do? You would get the cubed root. Now you guys remember what the cube root, remember when you take the square root, it's like it's raised to the power of 1/2. So when you get the cube root, it's raised to the power of 1/3. So when you put that in your calculator, if you use a little caret, you're going to raise it to the 3rd power. So I'm going to take the cube root of that, cube root of this, and I'm not taking too much time on how to punch it into your calculator. That's what I'm expecting you guys to know from your math class. And we do that, and here's what we're going to get. X is 0.16, and it's going to end up being molar. What did I just figure out? You guys, I actually figured out the value. Why is that? You'd say, well, I just figured out X. I figured out that's the concentration of my lead ions in solution, right? That was my X. I designated that X. Well, look, it's a 1-to-1 ratio. So for every one of this that's dissolved, that's how much, I'm sorry, one of this that's in solution, that's how much of that dissolved. So what is the molar solubility? 0.16. Oh, no, you know what? I actually got it wrong. I was wondering that because I know it's so insoluble. 0.016 molar, you guys can see. So basically at 25 degrees Celsius, this is the concentration I'm going to get of a saturated solution. Once it's saturated and the maximum amount of ions are dissolved, that's all that is dissolved. And so what would we call lead chloride? We'd say it's relatively insoluble. Basically, you guys, if you get a molarity that's like less than 0.1 moles per liter, that's how much would dissolve, you'd pretty much say it's insoluble. And that is pretty consistent with such a low KSP value. So, you guys, that allows you to predict. So if I had lead chloride and I put it in water, I'd expect very little bit to dissolve. Now there's the common ion effect. If one of the ions in a solution equilibrium is already dissolved in the solution, then what will happen when you dissolve the compound? So like, right, we have this, barium sulfate's going to dissociate to a certain measure. Sulfates are relatively soluble, so maybe we'd expect the KSP to be much higher than the KSP was for lead chloride. So what would you expect if you try to take some barium sulfate and you put it in a sodium sulfate solution? Right? So we're not just dissolving it in pure water, we're dissolving it in a solution that already has sodium sulfate in it. Well, you would want to look for common ions. You see barium sulfate has a sulfate ion, and yet what do we already have in solution? If we're putting it in a sodium sulfate solution, we already have sulfate ions. So, wouldn't you guys agree, if we have extra sulfate ions, won't that cause there to be a shift in this reverse reaction to the left? And what's the result? Less of the barium sulfate is going to dissolve. More of it's going to stay in its associated precipitate form. Okay, you guys, right? And the reason why we're talking about this in our acid-base equilibria unit is because pH can also affect the solubility of salts. This says if a substance has a basic anion, it will be more soluble in an acidic solution. Okay, so for example, let's say that we've got magnesium hydroxide. Magnesium hydroxide is relatively insoluble, so it means it heavily favors the left side, right? So, but some of it will dissociate into magnesium ions and hydroxide ions, okay? So this is what it's saying, if it has a basic anion, so that would be a basic anion. So what it's saying is, now imagine if you put this in a acidic solution. If it's acidic, right? Just imagine you have H plus ions, right? A larger, relatively large concentration of H plus ions, let's just say in an acidic solution. What do you guys think would happen? What are the H plus ions? You guys remember what we always want to see is what could it interact with? Wouldn't you guys agree? Whenever you guys see H plus and OH minus, what are you guys thinking? You're thinking, oh, they neutralize each other. Wouldn't those combine together to form very stable water? So what's the effect of putting it in an acidic solution? What's going to happen is there's going to be a reduction in the hydroxide ions as those combine with H plus ions to form water. And so if I'm removing the product, what happens to the equilibrium? Isn't it going to shift to the right? And as it shifts to the right, what's happening? Isn't more of it going to dissolve? So if I take a salt with a basic anion and I put it in an acidic solution, I'm going to expect to be able to dissolve more than if I were to just put it into water. Okay? let's look at the flip side. What if I had, in a basic solution, substances with acidic cations are more soluble in basic solutions. So now let's look at this when we say an acidic cation. So just think about cations, right? You guys know those positive ions. Well, think about it if this was in a basic solution. So we have OH minus ions present. What could those OH minus ions potentially interact with? Wouldn't you guys agree? You're always thinking the opposite charges. Couldn't the zinc and the hydroxide come together and to some measure combine to form zinc hydroxide, right? So what's the effect of adding this to a basic solution? Some of that hydroxide ion will combine with the zinc ions, pulling the zinc ions out of solution, forming this insoluble. That's an insoluble, right? It would be relatively insoluble. So what the effect is, you're reducing the amount of zinc ions present. What's going to be the result? According to the Chatelier's formula, is it going to shift to minimize the disturbance? The disturbance was pulling zinc ions out of solution, so it's going to shift to the right, and in effect, more of your zinc chloride dissolves. Okay, and so that's what you would expect in a basic solution. Okay, well, precipitate form in a solution, when you dissolve a solid, you guys know a Q. You remember Q are just whatever values you have. You don't necessarily know if it's at equilibrium, but if you take your Q values and you put it in the equilibrium expression, and your Q value ends up equaling the KSP, the established KSP value at that particular temperature, then what can we say? The system is at equilibrium and the solution is saturated. You guys remember what we mean by saturated? When you take a salt and you put it in water, once you've reached the point at which the maximum amount is dissolved, right, which would be determined by the concentration of these, right? So if we take the concentration of these according to the equilibrium expression and it's equal to the KSP, then our Q value is equal to KSP. It indicates the maximum amount is dissolved, our solution is saturated. But now let's say if you had a situation where you had some values and you put it into the equilibrium expression, and then the value you got was less than KSP. Let's say we put some values in for lead and chloride, and it's less than 1.7 times 10 to the negative 5. What does that tell you? That tells you these concentrations here are less than they would be at the saturation point. And so that tells us our solution at that point is unsaturated and more can dissolve. Like, wouldn't you guys agree that these values would be less? Therefore, the reversible reaction is still going to the right. It's still shifting to the right until the Q value ends up equaling KSP, right? So at this point, that would indicate you have an unsaturated solution. And then you guys could probably guess the last scenario. What happens if you have a Q value, you plug values in, and you get a value that's greater than KSP? What would that indicate? So let's say I gave you some lead ion concentrations and then chloride ion concentrations, and then we just plugged it in, and then we end up getting a value that was more than 1.7 times 10 to the negative 5. What that tells you is these concentrations are greater than would be expected under a condition of saturation, and therefore what that tells you is you are indicating a concentration greater than what would be expected at that particular temperature. So what's going to happen when you add all that salt, some of it's going to come out. Basically, you're going to have a shift to the left, right? And some of it's going to come out, it's going to reassociate and come out as an insoluble salt. So the salt will precipitate until Q. Once again, it's always going to go until right, this Q is equal to KSP, because that's the point at which it's reached equilibrium. Okay, you guys, we're going to finish with one practice problem. So what would one observe upon adding 2.0 times 10 to the negative 3 moles of calcium fluoride to 1 liter of water? And I give you the KSP value, okay? So, right, we should be able to write our reversible reaction. We got calcium fluoride, some of it dissociates into the aqueous ions. Once again, if you're given the KSP value, I would write a KSP expression. Or you know what? Actually, in this one, I mean, I can see where you do that. No, let's just do it. But you guys, let's use values that they gave us. So we have values, but you know what? At this point, let's say we don't know if it's at equilibrium. So what are we going to call it? We're going to call it Q. It's set up the same way. What is our Q expression? You guys, right? Wouldn't it be the concentration of calcium ions times the concentration of fluoride ions, but then you got to square it, right? So that's what we got. So now let's just assume all of it dissociates. Let's assume full solubility. So if that's the case, if I had 2.0 times 10 to the negative 3 moles of calcium fluoride, notice it's in 1 liter, so it makes it really easy, because remember, these are all concentrations, so it's per 1 liter, so it's all the same. If this was in 2 liters, you guys see what I'd have to do? I have to take this value and divide by 2. But a lot of times it's done to make things a little easier for you. So let's say it fully dissociates. Well, if I had 2 times 10 to the negative, right, look, for every one of this, I get one of this. So wouldn't the concentration of that be 2.0 times 10 to the negative 3? Well, for every one of this that is formed, I would form twice that. So wouldn't I, when I go 2 times 2.0, which would be 4.0 times 10 to the negative 3. But then you guys got to remember, don't forget, you have to also square it. Sometimes people think when they double it, they forget about squaring it. And so then I'm going to calculate my Q value, and I calculate it. I already did this ahead of time. I'm going to get 3.2 times 10 to the negative 8. That's my, and you guys notice there's no units because it's a K, equilibrium expression, or a K value. Now this is my Q. So then what am I going to do? I'm going to compare that to the K. You guys, if that was equal to that, then I would know, oh, it's saturated, it's reached equilibrium. But what do we see? We see this value. Hopefully you guys know, look, 10 to the negative 8, this is 10 to the negative 11. Hopefully you realize that this value is much greater, on the order of 3 factors of 10 greater than that. This is a larger number. So our Q, in this case, is greater than our K. So what we're saying here is, these concentrations are way too high. You would not have these concentrations dissolved in solution. They're way too high. What that tells you is this is too much. So what's going to happen is you're going to actually have a shift to the left. So what's going to happen is with all this calcium fluoride, some of it is going to come out of solution. So when you take all this and you put that much calcium fluoride in 1 liter of water, some of it will dissolve. But once again, these concentrations are too large, because we see our Q value is greater than K. So that tells you there's going to be a shift to left, and some of it's going to precipitate out or remain as a solid. So that's what we expect. So you guys see kind of the power is, you know, I could perform this beforehand. I don't even have to have my calcium fluoride. I know if I had that much calcium fluoride, I put it in water, I would expect some of it to dissolve, but then I would expect to see some of that calcium fluoride to be sitting at the bottom of the beaker in an insoluble state. All right, guys, that's it for today. Until next time.